So, good afternoon, everyone. I'm Mariya Shajan. I'm a research scholar from BITS Pilani, Hyderabad campus in India. I'm grateful to present my research work titled Dynamic Fracture Analysis of Functionally Graded Material through Adaptive Phase Field Simulation. And this work is carried out under the supervision of Professor Raghu Piska and Professor Sundarraj Natarajan. So, this is the outline of my presentation. So, starting with the motivation and the objective that drove this study. Next, I will follow that. I will introduce the methodology focusing on the dynamic phase field model. Then, I will explain about the integration of the adaptive finite element with the phase field model, followed by the validation of the proposed adaptive phase field model with the results. Finally, the summary and the conclusions. So, starting with motivation. So, what do you mean by functionally graded material? Functionally graded materials are advanced composite materials in which there is a gradual variation of material properties throughout the over the dimension, which we can use the properties of the corresponding material. And these functionally graded materials are commonly used in the aircraft components to resist the thermal stress from higher temperature to the uh, lower temperature. So mainly they will have ceramic at the inner surface to resist the thermal stress from the high temperature environment, and in the inside you will be having the metal to resist to provide the structural integrity. Even though FGMs are having numerous advantages, the main challenge associated with the FGM is that because of the gradual variation of the properties, it will introduce complexity in the fracture behavior. So our next question is how to model the fracture propagation problem. To model fracture propagation, we are having different approaches. And one among them is the phase field method. And this phase field method has recently emerged as a prominent and widely adopted technique due to its robustness and versatility in accurately predicting the fracture behavior. And the numerous advantages of the phase field method are it can be used to track the branching, propagation, and the interaction of the cracks, and there is no need of predefined crack and the criteria for crack initiation like the methods in LEFM model. Even though phase field method is having the advantage, the challenge associated with the phase field method is that it requires fine mesh to accurately capture the small scale features of the crack, resulting in computationally expensive. So, my objective is to develop and validate an adaptive phase field model to enhance the computational efficiency by accurately predicting the crack growth. Meaning, what you mean by adaptive phase field model is that where the crack propagates, there I will be having the finer meshes, and away from the crack, I will be having a coarser mesh. And I will use this adaptive phase field model to study the crack propagation in the functionally graded material under the dynamic load under a different scenario. So, moving on to the methodology part. So, to model fracture, we are having different approaches. Mainly, we are having discrete crack approach and continuum approach. The difference lies in these two approaches in which how we treat the crack. So, starting with the discrete crack approach. Here I have shown a representative domain omega with a crack capital gamma, and it is subjected to the boundary conditions like displacement and the traction boundary condition. So, in the discrete model, the discontinuity is represented by a sudden jump which is having value 1 at the crack. So, in the means here we will be having the energy function which is the summation of the elastic strain energy and the external energy. And if you are having a crack, we will be having an additional term that will be the fracture energy term. And in the discrete crack model, we will integrate it over the crack domain omega, and GC is the critical energy release rate. So coming to the phase field model. So in the phase field model, the discontinuity is represented by a is smoothed over such that a smooth transition can be described using a field variable phi, which is having value 1 at the crack and 0 at the other locations. And L0 is the length scale parameter over which the sharp crack is diffused. If the L0 value is large, you will be having a thicker crack, and if L0 value is small, you will get a sharp crack. So in the phase field model, the energy functional equation will be like this. So you will be having a G of phi which is multiplied to the strain energy term. That is G of I is the stress degradation function, meaning whenever we are applied the load, how the degradation of the stiffness is reduced will be chosen by this G of I. And the fracture energy term is integrated over the whole domain omega, and it is multiplied with the psi of I, which is the crack surface density functional. So in the phase field model, you will be, this is the discretized equation, you will be having the momentum equation. This is the governing differential equation, that is the momentum equation and the damage evolution equation. So this is the discretized weak form. So you'll be having two equations. We will solve these two equations in a um, alternative manner. So if you see that in the momentum equations, there is a second order derivative of the time. To solve that, we will use the Newmark's meter method for the time as the time integration scheme. So, to overcome the computational challenges associated with the phase field method, we will integrate the adaptive mesh refinement in the simulation process. So, for the adaptive process, we will use a systematic process, that is a solve, estimate, refine project. So, we will continue this process. So, I will explain what exactly this is. Suppose if we are having a coarser mesh having four elements. First, we will solve these momentum equation and the phase field evolution equation, and we will estimate the value of the phase field variable at each element, and we will compare with the criteria with the, that is the criteria is if the phase field value that we have obtained at each element is greater than the threshold value, we will divide or refine that element into child elements, meaning here we will be having a quadri decomposition, meaning each element is parent elements divided into four child elements. So here if you see, you can see that the third element is refined into 10, 9, 3, and 8. And whatever the value that you have obtained from these parent element will be projected to the child elements, and this process will continue. So this figure shows the zoomed view of the crack tip. Here we can see that a quadri decomposition of the elements is occurring. The main issue with the quadri decomposition is that it will result in hanging nodes between the adjacent elements. And with the standard finite element, we can't solve this because of the compactability issues between the elements. To uh, accommodate with the hanging nodes, we will use the help of the polygonal finite element, meaning each element we will treat as the polygonal elements. And different kinds of polygonal interpolants are there: Wedge press, mean value, Laplace, and all those things. In this study, I have used the mean value shape function because it can be used for both concave as well as the convex polygon. So this figure shows the a polygonal element with the hanging nodes, and here this shows the equation for the mean value shape function. Next, I will move on to the validation of the both adaptive phase field method as well as the implementation of the FGM under the dynamic load. For that, I have chosen a three-point bending scheme subjected to dynamic load. So this specimen is subjected to a traction load of sigma 0, a constant traction load. These are the material properties used, which is having different material at top and bottom, and it is the material gradation is a linear gradation. And this is the comparison of the crack path observed from my present simulation as well as the experiment. And here we can see that it is exactly matching with the experimental results from this paper. And this is the adaptive mesh and the damage profile generated. Here we can see that where the crack propagates, you can see that there will be a finer mesh, and away from the crack, you will be having a coarser mesh. Okay, this is the video showing how the crack is propagated along the path. You will be having a finer mesh. Next, I am just showing the comparison of the number of elements required for both uniform and the adaptive mesh. So here we can see that for the uniform mesh, you require a 1,23,000 elements, whereas for the adaptivity, you require only 11,272 elements. So if we compare the efficiency, we can see that with the adaptivity, we can achieve a 90% efficiency by reducing the number of elements. Next, I'm just moving on to the investigate the influence of the several key parameters on the dynamic fracture behavior of the FGM. For all the cases, I have chosen a edge crack plate subjected to traction load at top and bottom. And this is the geometry and the loading condition. So starting with the influence of the gradation form. So here I have applied a constant traction load of 15 megapascal at the top and boundary, top and bottom. And these are the material properties. Material one will be the metal and material two is as the ceramic. And for the gradation form, I have used linear, exponential, and sinusoidal function. These are the equations for that. And this figure shows the variation of the elastic modulus uh, uh, through the y-axis. And this is how the crack is propagated at the final load step till 90 microsecond. The specimen is subjected to traction load. And here we can see that till the branching happens, you will be having a similar crack pattern. Once the branching happens, you'll be having a different kind of crack profile, which shows the importance of the correct gradation form. And here also we can see that for the exponential, we will be having a higher elastic energy. And once the fracture happens, the dissipated energy also is increasing. Next, moving on to the influence of the gradation direction. So for that, here I'm taking three cases. Case one as the gradation across notch, and case two and case three as the gradient along the notch with pre-crack on stiffer material and pre-crack on the compliant material. Stiffer material meaning having higher Young's modulus. So here we can see that all the three cases you will be having a different crack path. And if we check with the case 2, which is having pre-crack on the stiffer material, you'll be having secondary cracks are developing. And when the case go into the case 3, which is the pre-crack on the complaint material, here you can see that the secondary branching is happening and then it merges and then it propagates and then you will be having a tertiary crack. Next, moving on to the influence of the load value, meaning at the what is the traction load? If it varies, what will happen? So it is varied from 10, 15, 20, and 25 megapascal. So here, if we check, we can see that with the 10 megapascal, here we have seen that there is a secondary branching and at the bottom you are having the ceramic. So ceramic which is having the lower fracture toughness, so more crack is going towards the ceramic area. And if we increase the load value, we can see that multiple branching is happening. And with the dissipated energy also, we can see that the increase in the load value, there is increase in the dissipation energy. Next, moving on to the influence of the biaxial loading. How the biaxial loading rate means at all the direction, if you are having loading, how it will affect. So for that, I have chosen the biaxial loading rate as sigma 0 by sigma cap 0. And the values are varied from 0, 0.5, 1, and 2. So k equal to 0 meaning you will be having only at top and bottom the loading condition. At right and left, you will not have any loading condition. So this is the corresponding crack profile obtained. Here you can see that with the increase in the biax, biaxial loading rate, multiple branching is happening and the crack bifurcation angle is closer to the initial crack tip as we increase the biaxial loading rate. And once the K value is equal to 2, the crack bifurcation angle is almost equal to the 90 degree. And the dissipated energy and the elastic energy is also increasing with the increase in the biaxial loading rate. Finally, the influence of the load type. For that, we have chosen constant, RAM, and the triangular loading, meaning at the constant, you will be having a constant traction at the top and bottom. For the RAM, it is initially we will start from 0 and we will increase till 45 microsecond, then we will kept it as constant. And in the triangle, we will increase, then we will decrease the loading. So this is how the crack profile is obtained. Here we have seen that by changing the load type, the crack path is also means the crack propagation rate as well as the crack branching type is changing. So the same kind you can observe from the energy graph. So finally, the summary and the conclusions. So to overcome the computational challenges associated with the phase field method, we have used the adaptive meshing. Here we have combined the quadri decomposition and we have seen that the computational cost is reduced. And the implementation of the adaptive PFM under the dynamic loading in FGM we have done, and we have validated with the experimental results and it's matching with the experiment. Next, we have done the investigated the influence of the gradation forms, gradation direction, load value, biaxial loading, and the load type. And the conclusions we obtained are that with the change in the gradation form and the gradation direction, the crack path will change. And with the increase in the load value and the biaxial loading rate, we can see multiple crack branching is happening. And when the load type is changing, the crack propagation rate as well as the crack branching type is changing. So whenever we are doing the construction of the functionally graded material, we have to take care of all these parameters. So these are the conclusions that we have obtained. So these are the references. Thank you.